This is Module 3, Lesson 2 for Algebra 1, Functions. I'm following in the McGraw-Hill online textbook. So here's the main page. When you go to the course, and then I go to Module 3, Lesson 2, then start launch presentation. So your warm-up is name the ordered pair for each point. Okay, so for point E, there it is. What's that ordered pair? Okay, that's pretty straightforward. I'm not going to show you the answers. So when we're talking about functions, it's a relationship between our input variables and our output variables, or dependent and independent. We talked about that a little bit already in 3-1. So a website that recently looked at 6.3 million selfies posted on popular social media sites found that the most popular city for selfies was London, and New York City came in second. The other cities in the top 5 in order were Amsterdam, Paris, and Barcelona. The percent of the 6.3 million selfies taken in the 5 most popular cities can be represented by the relation in the graph. So we can see our graph down here. We can analyze the relationship between the dependent and independent variables to determine whether the relationship is a function or whether the relation is a function. So if you look at this in your McGraw-Hill, you can tap on each button and it'll tell you what's going on with the cities. I think I already did that. So if I look at what's city number 4, oh, that's Paris, 9.82% of all the selfies taken. Okay, just make sure I reset everything. Okay, so that just shows a relation. The vocabulary for 3-2 is, it's just two things. The first one, any day now, the first one is a function, a relation in which each element of the domain is paired with exactly one element of the range. We talked about domain and range last time. Function notation is a way of writing an equation so that it just looks like this: y equals f of x. And we say that as f of x, not f times x. That f just represents a function, and we just named it f. So it's f of x, a function, okay? There's one way to tell, a quick way, if you're looking at a graph of a function, that you can tell if a relation is a function, and that's called the vertical line test, okay? To test graphically whether a relation is a function, you can use the vertical line test. If a vertical line, so that's a line up and down, this green line, if it passes through more than one point in a graph, the relation is not a function, okay? So we're going to look through these examples to see if this is a function or not a function, okay? We can drag the vertical line to tell. So here's our function f of x equals negative 2x plus 5. Here's my green line. I'm just going to drag it. Now notice where the green line intersects the graph of our function, the blue line, at the dot. It's only touching at one place at a time, the whole way. Now, if it's a function, that means what? It only intersects one time. If it intersects more than one, not a function. Let's look at another one. Relation 2. Look at my vertical line test. It's touching one time, oh, black dot. Still only hitting one time, even though it's curvy. Okay. Now notice this is g of x. We just named this function g. It's different than the function that we saw before. We just called that f of x. This is just function g of x. Let's look at another one. Here's a circle, and there's the equation for our circle. Let's look at our vertical line test. What is going on here? What are these two dots where it intersects the circle? My vertical line intersects the circle in two places at once, except for right there on the, can't make it touch right there, but nope, right. I can't make it touch one time. That's tricky. One time. Oh, I can't do it. But so what does that mean if it touches in more than one place? It means it is not a function. And that is a perfectly normal circle that never hurt anyone. Hurt anybody. It's just not a function. It's just not a function. It's still a circle. It's still okay. It still has value. Look at this next one, vertical line test. Is that a function? Yes. Vertical line test. You can look right at it and kind of tell, uh-oh, what's going on here? Look at this function, this sideways parabola. It's touching two times. I almost, I did it. I made the dot touch once. Okay. Still, vertical line test applies across the whole graph of your function. Touches more than once. Not a function. All right, this one. Oh, this is just a straight line. J of x equals 7. Still only touches one time. Function. What about this one? Can you tell? That's a function. One time. One time. That's an absolute value function. That's what that looks like as a graph. And then our last one, this is a little curvy line. P of x is x to the 1/5. You can have fractions as exponents. We're going to talk about that later. Yeah, still a function. Okay. So vertical line test is just an easy way to tell if a relation is a function. We look at the graph, draw a vertical line, and you can use a pencil as a vertical line and slide it from side to side along the graph of your function and see if it's a function or not. We already did these exercises, I believe, for each, which the ones are function. You select all that apply. We already said which ones were functions or not. Exercise 2. What did you notice about the relations you decided were functions? What did you notice about the relations that you decided were not functions? Okay, can you look at one and tell if it's a function or not, and what looks different about the ones that are not functions? For example, that's not a function, and that's not a function. So just think about that. So let's learn about functions. Again, a function is a relationship between input and output, okay? Or between our independent variable and our dependent variable, for example, okay? So we can look at our picture right there, right? Where it says, look at our domain. We did this in 3.1, our domain and our range. So now we're seeing a mapping and a graph of the function. Remember, a function is a relation in which each element of the domain is paired with exactly one element of the range, okay? Exactly one element. I'm trying to draw with my little annotation thing. Hang on, I can't get to it. Okay, so here's our domain right there. Oops. Whoops, I messed up my screen share. Here's our domain, right? And our range right here. Now, remember, function each element of the domain is paired with exactly one element of the range. Okay, looks okay here in our mapping. Okay, I think that works. Let's hold on. Hold on. Let me pause for a second. I got all kinds of stuff going on. My daughter's coming in, making all kinds of noise. And I don't know how to edit the videos. Y'all know that's beyond my capability. Okay. Let me clear my drawings. Clear my drawings. I may have to pause and tell my daughter to just chill out while I'm trying to record. my video. Oh my goodness. Okay, so let's move through these slides to see if we can tell if each relation is a function. Okay, so remember, every element in the domain is paired with exactly one element of the range. Okay, so -4 is mapped to -1, -2 is mapped to 3, +2 is mapped to 3, and 5 is mapped to 6. So is this a function? It is. Now, remember, hold on, just because we have one element in our range where two different things are mapped to it, that's okay. We're focusing on the domain side. -4 only goes to one other number. -2 goes to one number. +2 goes to one number. And 5 goes to one number, right? If my function, let's say I've got a function machine, right? Here's my function machine. Function machine. Machine. If I put one thing in, I'm only going to get one thing on the other side of it. Okay. Now, I could put, if my function says whatever I put in, it's going to equal 3, no matter what I put in, 270, just because I get 3 on the other end, okay, I'm only getting one output for every input. Now, if here's my function machine, right? Okay, that's a better function machine. And say I put a 2 in and it goes through the function and I get a 7 and a 12 coming out, that's not a function. Okay, that's not a function. To be a function, every element in the domain is paired with exactly one element in the range, not two different things, only one. Okay, all right. So let's look at another example of a mapping. Let me clear my drawing. Clear my drawing. So let's see this. Now this is set up like a table. Okay, so there's our domain and there's our range. If I put in a 2, I get out a 3. But wait a minute. And then I put in a 2 right here and I get out a -3. That's not allowed. If I put in a 2, I'm only allowed to get one thing on the output side. So that's not a function. That is not a function. Now this time we have a set of ordered pairs. Okay, so let's look at our domain. Okay, so we've got 2, we put in 2, we get 5. We put in 4, we get 7. We put in 8, we get 11. We put in 4, wait, did we already put in 4? What is this foolishness? If we put in a 4, we can't get a 7 and a 13 on the outside to be a function. Every element in the domain is paired with exactly one element in the range. So that's not a function. Not a function. Okay, let's look at our next resource. Now, you can go through these slides by yourself. You can even make the thing talk, for example. Hold on, let me show you. So right here, you see this little microphone button? You can have it read it aloud for you. Let's listen.
Identify functions. Determine whether each relation is a function.
So you don't have to listen to my voice, but I promise you that robot voice has no jokes. None. So if you don't like my jokes, that's fine. You can listen to the robot voice. So let's determine whether each relation is a function. Let's look at A. Okay, so 2 mapped with 5. 3, look at 3. 3 is a little frisky. 3 is mapped with 5 and 0. That is not cool. That's not a function. Not. Let's look at this one. Okay, -2 is mapped to 8. -1 is mapped to 2. 0 is mapped to 8. 1 is mapped to only 4. 2 is mapped to only 2, right? Every element in the domain is mapped to only one element in the range. So that is a function, okay? All right. Let's look at another example. So, 5 schools are competing in the long jump portion of a track meet. The distances of the players with the best jump on each team are as follows. Team 1 jumped 20.6 feet. Team 2 jumped 21.5 feet. Well, we can tell. We can look down here and see how far everybody jumped. Okay, great. So in part A, we want to make a table to represent all these values. So let's do that. Let's make a table. So we're going to map each element of our domain to an element in the range. As soon as we stop spinning, there we go. Okay. So team number 1 jumped 20.6 feet. We got that. Team number 2 jumped how far? 21.5. Just making a table. If you can make a table, man, that just makes everything so much easier. Team 3, 20.9 feet. Team 4, 19.4 feet. Team 5, 20.2 feet. Okay. So we're showing the relation between the team and their best jump. Okay, so we did our table. That's looking pretty good. That's looking pretty good. We're right. All we have to do is type the numbers in there. Part B. Oh, what's the domain and the range? Well, look, we already have it set up. I'm going to show you yet. We already have it set up on our table, right? The domain, our independent value is the team number, right? The team number doesn't depend on how far they jumped, right? It's not dependent on anything. It's just our team number. The best jump depends on which team it is. So the best jump is our dependent value. So our domain is 1, 2, 3, 4, 5, that set of numbers. Our range is these values, 20.6, 21.5, 20.9, 19.4, and 20.2. And you can see that here. Okay. So part C, determine whether relation is a function. Well, yes, it's a function. For every element of the domain, there is exactly one element of the range. So the relation is a function. So if I put in team number 1, I can get 2 different distances. That would not be a function. Okay. So this is a function. Let's look at another example of analyzing our data. Madison took 5 quizzes this semester. Her scores on the quizzes are as follows: 86, 92, 78, 86, 84. Okay, determine the domain and range of the relation. Okay, so we want to drag the correct numbers to the boxes. So what's our domain, you think? What are our input values? I'm thinking 1, 2, 3, 4, and 5, right? Quiz 1, quiz 2, 3, 4, and 5. Let's see if I can drag these over. 1, 2, 3, 4, and 5. And then the range the range is the set of test scores. Quiz 1, 86. Quiz 2, 92. Quiz 3, 78. Quiz 4, 86 is already in there. Quiz 5, 84. Okay. We don't have to put 86 twice. We already talked about that in 3-1. We just put it one time. All right, cool. Next resource. Now let's look at equations as functions. Equations as functions. We're familiar with equations. We're just going to look at them in a little different way. Okay. Equations can represent both relations and functions. Every solution of this equation is represented by a point on the graph. So there's a graph of our function, that blue line. The graph of an equation is the set of all of its solutions, okay? Which usually forms a curve or a line. In this case, it's a linear function. It makes a straight line. We can tell it's a function because we're doing the vertical line test right here, right? It only passes through one point at a time on the graph. So the graph and the equation represent a function. Ooh, do we know the domain and the range of this function? The domain is all of our possible input values or independent values on our x-axis. What are all the possible x values for this function or this equation? What are all the possible things I could substitute for x? What are all the possible numbers? Same thing for the range. What are all the possible numbers I'm going to get as y values when I put in some x value? Think about that. Is there anything that I can't put in there? Let's look at another one. Is 4x minus y equals 17 a function? Well, okay, we graphed it right here. Does it pass the vertical line test if I take my pen or pencil, make a straight line up and down and go side to side? Does that my vertical line and the graph intersect in more than one point? Just one point. So that is a function. So yes, for each element of the domain, there's only one element of the range. Now, sometimes on multiple choice, you'll see two yes choices, right? But the words will be wrong, right? It'll say yes, for each element of the domain, there's only one element of the range. The other yes one will say yes, for each element of the range, there's only one element of the domain. That's not the definition of a function, okay? It's got to be like this. For every element in the domain, there's one element of the range, okay? Be careful. So you have a check assigned to you in McGraw-Hill, okay? Not in Alex, in McGraw-Hill in your textbook. So go ahead and do that check, or you can wait until after this lesson is over, but do the check because I'm going to check to make sure you did it. So let's learn about function values. Now, we're familiar with equations. Equations that are functions can be written in a form called function notation. Function notation, okay? Function notation is a way of writing an equation so that y equals, remember how we say this? F of x, not f times x. We call that f of x. It's f of x, okay? That's how we say it, f of x. Okay, tap on each card to see each equation and function notation and see if you notice something about these. Okay, so let's look at card number 1. Y equals 5x minus 3. Flip it. Look at the function notation. F of x equals 5x minus 3. Okay, let's look at number 2. Y equals 2/3 x plus 12. Look at the function notation. How is it different? My equation didn't change. The only thing that changed, instead of saying y equals something, we just made it f of x equals the same thing, okay? Because y equals f of x, okay? Instead of saying y equals 7x plus 2, we say f of x equals 7x plus 2. That's just in function notation if it's a function, okay? That's the only difference. Only difference. Okay. What's the function notation for y equals 14x plus 8? See if you can figure that out. Okay. Let's see if we can find some function values. Oh, suppose you want to find the value in the range that corresponds to the element 8 in the domain. Okay, so we know there's an element 8 in our domain. We want to know, well, what's the one that it matches up to in the range? If my x is 8, what's my y value? Okay, now that's written f of 8, okay, because my x value is 8, f of 8, and is read f of 8. The value f of 8 is found by substituting 8 for x in the equation. Remember when we did, like if we said y equals negative 2x plus 9 when x equals 8, it's the same thing. You just substitute 8 for x in the equation, okay? So see if you can find f of negative 6. We're going to substitute negative 6 back in our equation and find the value. So it'll be negative 2 times negative 6 plus 9. There we go. There's a fly in here. What on earth? It's winter. Where did a fly come from? Now, look at this next one, f of 4 plus 3. There's still our f of x, negative 2x plus 9. This time we still substitute x with a 4, but we still have to do f of 4 plus 3. okay? X equals 4. We did f of 4 plus 3. We added 3. All we're doing is substituting our value of x in our equation. Now look at this. See, f of 5 minus f of 1. We substitute 5 for x in the original equation, right? So negative 2x times 5 minus 9. Then minus f of 1, okay? F of 1, we take that equation and substitute a 1 for x in the equation. And then we just do our order of operations and solve. Okay, it's not bad. It's not bad. Is f of 3 minus f of negative 2 the same as f of 3 plus f of 2? You may think that's the case because you see these two negatives together. This is not f times negative 2. It's not. F of negative 2 means we substitute negative 2 for x in our equation. So they might be the same. They may not be the same. You might want to check that out. Let's look at another example of finding function values. Okay. For f of x equals 4x minus 12, find each value. So we want to find first f of 5. Okay, f of 5. So that means we put a 5 in where there's an x. Let me draw. Okay, so f of 5 would be 4 times 5 minus 12. Okay, f of 2 minus 4, we substitute 2 in there, right? Would be 4 times 2 minus 12. That's our f of 2, right? Then don't forget minus 4. Okay. F of negative 3 plus 8. F of negative 3 plus 8 is, okay, 4 times negative 3 minus 12. That's just f of negative 3 by itself. Then I have to do plus 8. Plus 8. Okay, be careful. F of 1 plus f of 6. Okay, f of 1 is 4 times 1 minus 12. That's f of 1. Okay, plus f of 6 is 4 times 6 minus 12. I want to keep those separate. And then I just use my order of operations and I figure that out. Right? Take some time and work on those. See if you can figure those out. And see if you can get those right. You can go in your McGraw-Hill and do the same thing. Okay. Let's look at our resource. Oh my goodness, this fly is driving. All right, so let's, evaluating some functions. Look at these. H of x, and the letter is h is just a variable that we give it. This is a function h. That's just what we decided to call it. Okay. H of x equals negative 6x squared plus 18x plus 36. Find each value. So for h of 2, we're going to substitute a 2 wherever there's an x. That's it. Okay, and that shows you how to do it. The next one, h of 4 minus h of 1. We're going to substitute a 4 in our equation first, get that settled, and then substitute a 1 in for x. Okay, we'll do h of 4 minus h of 1. And that's what it looks like. Now, h of 5 minus 7. Okay, I want you to work on that by yourself and see if you can get the right answer. Hold on. See if you can get the right answer. Pause the video, work on it, and then see if you get negative 31. Okay. Even if you already know the answer, see if you work on it, see if you can get the same answer. Okay. Ooh, look, find h of 3, then find h of negative 3. What's the same and what's different about those? Interesting. So here's another example evaluating functions. For g of x equal to 3x squared plus 12x plus 9, find each value. G of -8, g of 5 plus g of 2, and 4 times g of 7. Ooh, look at C. That's going to be 4 times g of 7, not 4g times 7, okay? It's 4 times g of 7, okay? See if you can solve those. See if you can solve those. Watch out. What are we watching out for? Part C. Find g of 7 first, then multiply by 4. Yeah, that's good strategy. Now, if you need help, there's a video down here. Watch this video to review how to find nonlinear function values. Okay. I'm not going to play the video. Okay. You can find it in McGraw-Hill in this presentation. Okay. I'm on resource 17, slide number 17. Okay. See if you got those answers right. I didn't put my answers in. Will it check if I didn't put it in? No. Oh, you're going to have to figure it out. Now let's talk about interpreting function values. So we know what the value of the function is. What does that mean in real life? Okay, Mason works at the movie theater after school. The function g of x equals 9.25x represents the amount of money he makes before taxes for each hour that he works. So he makes $9.25 an hour, okay? Evaluate and interpret the function for each value, okay? So A, g of 8, okay? That means x is 8. That means he works 8 hours. So g of x is, there's our function value, 9.25x. So 9.25 times 8, which equals 74. That means it's going to make $74. Okay. G of 14, 9.25 times 14, which is 129.50. I think you get the idea. G of 27.5. If he works 27.5 hours, he'll make 9.25 times 27.5. You're going to get a weird decimal. But remember, if you come up with a number that has 6 decimals, money doesn't work like that, does it? It doesn't work like that. You're going to end up having to round it off to 254.38. We don't pay in half a pennies. That's not a thing. All right. One more example of interpreting function values. Macy made an initial deposit of $250 into a bank account. Each month, she deposits $80 into the account. Assuming no interest, the function f of x equals 80x plus 250 represents the total amount of money she'll have in the account after x months, right? So every month she deposits $80. So after x months, it'll be 80 times x. She started off with $250. So that stays the same. That's a constant. So what's f of 9? So after 9 months, well, here's our function. F of x is 80 times x plus 250, which is substitute a 9 into the x. So 80 times 9 is 720 plus 250 is $970, something like that. Oh, that worked. Okay. So what does that mean, though? What does f of 9 mean? After what? After a month, after 9 months, f of 9, we substituted x for 9, right? X is the number of months, right? Money shall have in the account after X month. X is the number of months. So f of 9 means after 9 months. The total amount in the account will be, we already figured that out, $970. All right. Next. You have a check in McGraw-Hill on function values. Okay. It's in there as an assignment. You can see it, do it, find out if you got it all figured out. You also have an exit ticket assigned for functions. Okay. How can you determine whether a relation represents a function? How would you do it for a set of ordered pairs? How would you do it for a mapping and for a graph? How would you do that? Okay. Um, I'm not going to click show answer. I want you to put that in your composition book. How would you tell if it's a function? Okay. All right, that's it. I will see you all in class.